In the spring of 1939, a senior Air Ministry official put his conclusions in writing. The Rolls-Royce Griffon engine, he noted, was not required. The Merlin was sufficient. The Spitfire was sufficient. Britain had what it needed. He was wrong on every count. Within 18 months, the Merlin's development ceiling was in sight. The performance margins that had seemed generous in 1939 were being consumed by heavier armament, by additional radio equipment, by the constant demand for more speed, more altitude, more power. The engineers at Derby knew it before the Air Ministry admitted it. The Griffin had been sitting in a drawer since 1936, waiting for precisely this moment. But the engine that would ultimately power the Spitfire to 460 miles per hour, that would intercept the V-1 flying bomb over the English Channel at low level, that would fly Fleet Air Arm patrols over the Korean Peninsula and North Atlantic surveillance missions well into the era of color television, that engine came within a single procurement decision of never entering service at all. The real story of the Rolls-Royce Griffon is not the story of a great engine's triumph. It is the story of how Britain's most successful aero engine nearly strangled its own successor in the cradle, and what it cost to prevent it. The Griffon did not begin as a fighter engine. It began as a racing engine, and a dead one at that. In September 1929, the Supermarine S6 seaplane, powered by a Rolls-Royce R engine producing 1,900 horsepower, won the Schneider Trophy outright at Qualshot on Southampton Water. 2 years later, the S6B raised the world air speed record to 407.5 miles per hour. The R engine, a 36.7-liter supercharged liquid-cooled V12, was the most powerful aero engine in the world. It was also, by the terms of the Schneider competition, immediately redundant. Racing engines are built for one purpose, one flight, one result. The R was never intended for production. Rolls-Royce filed its drawings and moved on. Or so it appeared. The company that held those drawings had been reformed under new management in 1925, Ernest Hives. Later, Lord Hives had come up through the test department and understood something that pure engineers sometimes missed, that a racing engine's value lay not in the machine itself, but in the knowledge compressed inside it. Every hour of development on the R engine had purchased understanding of supercharger behavior at extreme boost of coolant systems under sustained high power of metallurgy at the margins of what aluminium alloys could then sustain. Hives did not discard that understanding. He warehoused it. In 1933, the design office at Derby began preliminary studies for what would eventually become the Griffon. The requirement was deceptively simple: produce an engine of roughly the same external dimensions as the Merlin, so that it could in principle fit the same airframe but with substantially greater displacement and, in time, substantially greater power. The target displacement was 36.7 liters, exactly the R engine's volume. This was not a coincidence. The Merlin, by contrast, displaced 27 liters. It was a different philosophy, a smaller, higher revving engine designed for refinement and incremental development. Both approaches were rational. The Air Ministry, which had funded the Merlin's development from 1933 onwards under Air Ministry Specification F.7/30, and its successors saw no reason to fund a parallel program. One engine per airframe class was the procurement logic of the era. The man most responsible for keeping the Griffon alive inside Derby was Cyril Lovesey, who led the engine's supercharger development program from the mid-1930s. Lovesey had worked on the R engine's boost systems and understood better than most where the limits lay. He was not a public figure. He gave no speeches. But the supercharger configurations he developed for the Griffon, a single-stage, single-speed unit first, then a two-stage, two-speed system that would eventually define the engine's wartime variants, owed everything to the knowledge built on Southampton Water in 1929. The formal go-ahead for Griffon development came in April 1939 under Specification 37/34 revised. By that point, 3 competing design approaches had been internally assessed at Derby. The direct drive fixed-pitch configuration was rejected in favor of a reduction-gear drive that would allow the engine to turn a larger, slower propeller. The initial production contract worth approximately £1.5 million. At 1939 values was placed in August 1939. 3 weeks later, Britain was at war. The engine had its contract. What it did not have was priority. To understand what the Griffin was, it helps to understand what it was not. It was not a scaled-up Merlin. The two engines shared a cylinder angle 60 degrees between the two banks of 6 cylinders, and both used ethylene glycol cooling. Beyond that, they were different philosophies in aluminium and steel. The Merlin turned clockwise when viewed from the front. The Griffon turned anti-clockwise. This single difference, a consequence of the gear train geometry chosen for the reduction drive, would cause more training accidents in the first year of Griffin Spitfire operations than any mechanical failure the engine itself produced. The Griffin was physically larger than the Merlin in every dimension that mattered. 36.7 liters of displacement a cylinder bore of 6 inches against the Merlin's 5.4. A dry weight of 1,490 pounds against the Merlin's 1,375. And a critical dimension that dominated every conversion discussion. The propeller shaft sat 4 inches lower, relative to the engine mounting points, shifting the entire thrust line of the aircraft and requiring a longer, broader undercarriage leg on any airframe that adopted it. Reginald Mitchell's original Spitfire had been designed with the Merlin in mind. Its narrow, elliptical wing and raked undercarriage were balanced around a specific weight distribution, a specific thrust line, a specific gyroscopic moment from the propeller. The Griffin disrupted all three. The question Supermarine's design team faced in 1940 and 1941, led by Joseph Smith, who had assumed the chief designer role after Mitchell's death in 1937, was whether the airframe could absorb the disruption without losing the handling qualities that made the Spitfire worth modifying in the first place. The answer, which took 18 months of progressive prototype work to establish, was yes, but not without cost. The torque characteristic was the most immediate problem. A piston engine of the Griffin's displacement turning a propeller at full power on takeoff generates a twisting moment, a tendency to rotate the entire aircraft in the opposite direction to the propeller's poon. The Merlin's clockwise rotation meant that on takeoff its torque pushed the Spitfire's left wing down and the nose to the left, a well-understood tendency that pilots corrected with right rudder. The Griffin's anti-clockwise rotation reversed this entirely. It pushed the right wing down. It swung the nose to the right. Pilots converting from Merlin Spitfires applied instinctive left rudder and immediately made the swing worse. The Air Fighting Development Unit at Wittering documented this problem in a trial report circulated in late 1942. The report is held in the AIR-16 series at the National Archives Kew. It noted that of the first cohort of experienced pilots transitioning to the Spitfire Mark 12, the Griffin's first production variant, a significant number had experienced uncontrolled ground loops on takeoff. Several aircraft were written off. No pilot was killed in these incidents, but the pattern was clear enough that a dedicated conversion program was established before wider service introduction. The Mark 12 itself was a remarkable aircraft for a narrow purpose. Powered by the Griffin III, producing 1,735 horsepower against the Merlin, 45's 1,470 horsepower at equivalent boost. It was faster than any Merlin Spitfire below 20,000 feet. At low level, where Focke-Wulf 190 fighter bombers were making hit-and-run raids on coastal towns, the Mark 12 was the only RAF fighter that could reliably catch them. 2 squadrons received it, number 41 Squadron at High Ercall, Shropshire, and number 91 Squadron at Hawking in Kent. Between them they flew the type operationally from April 1943. The performance data confirmed what the test pilots at Boscombe Down had reported below 10,000 feet. The Mark 12 was faster than the Focke-Wulf 190A by approximately 8 miles per hour. It was a narrow margin, but margins won interceptions. The political moat around the Griffin program was not built from lobbying or promises. It was built from those performance figures delivered at a moment when the Air Ministry had no other answer to the low-level threat. The Derby production line already committed to Griffin manufacture was the only pipeline available. Cancelling it would have meant accepting the Focke-Wulf's advantage indefinitely. The decision was made. The program had its champion. The Griffin Mark III had proved the concept. The Griffon 65 would prove the engine. The two-stage, two-speed supercharger that Cyril Lovesey's team had been developing since 1941 transformed the engine's upper-altitude performance. Where the single-stage Griffin 3 began to lose power above 15,000 feet, the Griffin 65 maintained full boost to 21,000 feet and sustained competitive output to 28,000 feet. The power figures were unambiguous: 2,035 brake horsepower at maximum continuous power settings against the contemporary Merlin 66's 1,705 brake horsepower. The Griffin 65 was not incrementally better. It was a different order of capability. The airframe that received it was the Spitfire to Mark 14. 1,054 were built between 1943 and 1945. The Mark 14 entered operational service with No. 322 Dutch Squadron at Dienland in January 1944, followed rapidly by No. 610 Squadron at Exeter and No. 91 Squadron Veterans of the Mark 12 at West Malling in Kent. The decisive test came in the summer of 1944. The V-1 flying bomb, the Fiesler FY-103, known to the Germans as the Vergeltungswaffe, one crossed the English Channel at between 300 and 400 miles per hour at altitudes between 1,000 and 3,000 feet. It was a small target, difficult to radar track reliably, and fast enough to outrun most operational aircraft in service with Fighter Command at the time. The Hawker Tempest could catch it, the de Havilland Mosquito could catch it under specific conditions, and the Spitfire Mark 14 could catch it more reliably than either at the altitudes where the threat was densest. Between June and September 1944, pilots of No. 91 Squadron alone, flying Spitfire, Mark 14S from West Malling, destroyed 184 confirmed V-1s. No. 322 Squadron accounted for a further 108. No. 610 Squadron, operating from Friston in East Sussex, destroyed 62 more. The combined Mark 14 tally across all Fighter Command FAV-1 operations stood at approximately 305 flying bombs, destroyed roughly 23% of all V-1s brought down by aircraft during the campaign. The figures mattered beyond the arithmetic. Each V-1 that reached London or its intended target carried an 850-kilogram warhead. Each interception represented at minimum the lives of those beneath the bomb's flight path. The Griffin 65 was not an abstract engineering achievement. It was a calculated defense of specific streets in specific towns. On the European air superiority mission, the Mark 14 was equally decisive. Its maximum speed, 439 miles per hour at 26,000 feet, exceeded the Focke-Wulf 190D9, Germany's premier high-altitude fighter, by approximately 10 miles per hour at that altitude. By 1945, Mark 14S were operating with No. 2 Tactical Air Force in the ground attack and fighter sweep roles over Germany itself, flying from airfields at Fassberg, Lübeck, and Schelle. The Fleet Air Arm adopted the Griffin through the Supermarine Spitfire. The Spitfire Mark 15, powered by the Griffin 6, entered service with No. 801 Naval Air Squadron and No. 880 Naval Air Squadron in 1945. The Spitfire 47. The definitive carrier variant, powered by the Griffin 87 or 88 with contra-rotating propellers, served operationally during the Korean War. No. 800 Naval Air Squadron flew Spitfire 47s from HMS Triumph during the opening weeks of the Korean conflict in 1950, conducting ground attack sorties against North Korean positions in support of United Nations forces on the peninsula. 13 confirmed sorties were flown in the first operational day alone, July 3, 1950. The contra-rotating propeller fitment on the Griffin 87 series deserves particular attention. By the mid-1940s, the engine was producing enough torque at full power to overwhelm conventional single-rotation propellers of any practical diameter. The solution, two coaxial propellers turning in opposite directions. Their torque reactions cancelling each other had been under development at Rotork since 1943. The Griffon 87 was the first British production engine to enter frontline service with this configuration. It was also, as a consequence, the most technically complex piston power plant ever operated by the Fleet Air Arm. At its production peak, 1944 to 1945, the Rolls-Royce facility at Crewe, supplemented by the Derby main plant and the Glasgow Shadow factory at Hillington, was producing Griffin engines at a rate of approximately 200 units per month. The program employed directly or indirectly the labor of some 17,000 workers across the Derby, Crewe and Glasgow facilities, with a further subcontractor chain stretching to component manufacturers in Coventry, Birmingham and Sheffield. The engine was not merely a technical achievement, it was a significant node in the industrial geography of wartime Britain, but the first shadows were already forming. By the time the Seafire 47 flew its Korean operations in 1950, the Gloucester Meteor had been in RAF frontline service for 5 years. The de Havilland Vampire was in production. The Hawker Hunter was in development. The age of the piston-engined fighter was already past not by ministerial decision but by the logic of thermodynamics. A jet engine produced its power cleanly without the mechanical complexity of pistons, valves, and superchargers. It could be scaled. It could be refined. The Griffin, for all its capability, was nearing the physical limit of what a piston engine the size and weight of an aircraft power plant could do. The Rolls-Royce accounts reflected the shift. By 1950, the company's R&D budget was dominated by the Avon and the Nini jet programs. The Griffin received no significant new development funding after 1948. There was, however, one final chapter, and it came from an unexpected direction. The Griffin did not die in the manner of the TSR-2 or the CVA-01. There was no single afternoon in the House of Commons. No minister rose to announce the figure wasted, no cancellation telegram. The engine's end came the way most natural ends come, by incremental displacement. Each step individually logical. The cumulative effect visible only in retrospect. The Spitfire production line at Castle Bromwich closed in October 1945. The last Spitfire, a Mark 24 Griffin powered, was delivered to the RAF in February 1948. By that point, the RAF was already converting frontline day fighter squadrons to the Meteor. The late Mark Spitfire, for all its performance, required a trained piston-engine pilot base, a specific ground crew competency, and a supply chain of components and consumables tied to an industrial production run that was winding down. Each of these represented a cost. The Meteor represented in the RAF's assessment a clean break. The air staff did not say the Griffin had failed. They said it had been superseded. The distinction was accurate, and it offered no comfort to the workforce at Castle Bromwich, where 12,000 people had been employed at production peak, and the redundancy notices were issued in batches through the autumn of 1945. The export market absorbed some of the late Mark production. India received Spitfire Mark 14 and Mark 18 from 1947, operating them against Pakistani forces during the First Kashmir War. Thailand, Egypt, and Syria acquired small numbers. The Royal Netherlands Air Force retained Griffin Spitfires until 1954. But these were tail-end sales, not a sustaining program. The unit cost of a late Mark Griffin Spitfire, approximately £15,000 in 1947 values, was competitive with early jet aircraft only on paper. In operational terms, the runway was shorter for the piston machine. The Griffin's final operational home was the most improbable, the Avro Shackleton maritime patrol aircraft. The Shackleton had been designed around surplus Griffin 57A engines, a variant developed specifically for the maritime role, fitted with contra-rotating propellers on all 4 positions. The aircraft entered service with No. 120 Squadron at RAF Kinloss in 1951. And flew continuous North Atlantic patrols in support of NATO's anti-submarine warfare posture through the 1950s, 1960s, and 1970s. In the Shackleton MR3, the Griffon operated in conditions no wartime designer had anticipated: 8 to 12-hour patrols over the North Atlantic at low level in sustained heavy vibration from the contra-rotating propellers in temperatures that swung from cockpit heat-soaked to North Sea ambient in a single descent. The crews who flew the Shackleton's final years number: 8th Squadron at RAF Lossiemouth, operating in the airborne early warning role until June 1991, described the Griffin in terms that were affectionate, profane, and accurate in equal measure. The engine was demanding. The vibration levels on the AEW.2 variant were such that crew members were limited to specific duty hours before mandatory ground rest. Bolts worked loose. Oil temperatures required constant monitoring. The maintenance burden per flying hour was, by the standards of 1980s aviation, extraordinary. Number 8 Squadron flew its last Shackleton sortie on July 1st, 1991. The Griffin's last bench run had been by that point a purely maintenance exercise. The engine had entered service in 1942. It retired in 1991. 49 years. No British military engine piston turboprop or jet has matched that record in continuous frontline service. The program did not die. It was simply finished. The final Griffin was turned off. The propellers stopped. The airframe was parked. No contract was terminated. No minister made a statement. No committee convened. The engine had done what it was built to do. Then it stopped. The Griffin's afterlife is traceable in 3 directions. The first is technical. The contra-rotating propeller work developed for the Griffin 87 and Griffin 57, a series fed directly into Rolls-Royce's post-war engineering culture. The coaxial drive geometry. The bearing load calculations. The vibration isolation problem solved across 20 years of Shackleton operations. This knowledge did not vanish when the last Shackleton landed. It moved through the engineers who carried it into the company's turboprop programs and eventually into the propulsion systems of the Rolls-Royce Trent family. The specific path is diffuse, as it always is in engineering institutions. But the competency was built on the Griffin, and competencies do not retire with the machine. The second direction is doctrinal. The Spitfire. Mark XIV's V-1 interception campaign of 1944 established a set of operational principles for low-level, high-speed target engagement under radar ground control that shaped Fighter Command's post-war intercept doctrine. The specific tactics developed by No. 91 Squadron and No. 322 Squadron over the Channel in the summer of 1944 were studied and adapted for jet aircraft. The Griffin did not write that doctrine. The crews who flew it did, but they flew it because the engine made the intercept possible. The third direction is the one least acknowledged in official histories. The Griffin demonstrated conclusively that an engine and airframe combination could be developed in parallel with a war rather than before it, and could reach operational maturity in time to matter. The Griffin was formally authorized in April 1939. It was in combat service by April 1943. 4 years under wartime production constraints, competing for machine tools and labor with the Merlin program, it was eventually intended to replace. That timeline and the institutional decisions that shaped it is a case study in British wartime industrial management that has never received the attention it merits. The human footnote belongs to Cyril Lovesey. After the war, Lovesey was appointed Chief Development Engineer for Rolls-Royce's Piston Engine Division, a title that by 1948 was already becoming a career cul-de-sac as the company's center of gravity moved to jets. He was not a figure who sought public recognition. His name does not appear in parliamentary debates or ministerial correspondence. Stanley Hooker, in his memoir Not Much of an Engineer, describes Lovesey as the most technically accomplished supercharger engineer Rolls-Royce produced in the piston era, and notes without sentimentality that the jet age arrived before the institution fully understood what it was losing. Lovesey continued at Derby into the early 1950s, contributing to the company's turboprop work, and retired quietly. He died in 1975. The engine he spent 20 years developing outlived him by 16 years. The honest verdict on the Griffin is this: it was not a triumph of planning. It was a triumph of institutional patience and engineering stubbornness over procurement logic that was at every stage technically correct and humanly wrong. The Air Ministry was not irrational in 1939 when it questioned the Griffin's necessity. The Merlin was genuinely capable. The Griffin was genuinely redundant until it was not. The officials who authorized it in April 1939 did not know a German fighter would arrive in the autumn of 1941 that the Merlin Spitfire could not catch at low level. They made a reasonable decision to fund development while retaining flexibility. What saved the program was not vision. It was the fact that the engine existed when the gap appeared. That is, in the end, what development programs are for. If you found this history valuable, give the video a like. It's the single best signal you can send this channel. And if you want more stories about the aircraft engines and decisions that shaped British military power, subscribe to UK Defence Archive. We'll see you in the next one. Somewhere over the North Atlantic on a grey winter morning in 1987, a Shackleton AEW. 2 of No. 8 Squadron turned onto its patrol track at 1,500 feet. 4 Griffin engines at cruise power contra-rotating propellers, beating the cold air in opposing arcs, still listening for submarines, still carrying the war. The engine was built to fight long after almost everyone had forgotten what the engine was.